There is a hole at the bottom of the Pacific Ocean, and this hole is leaking water upwards.
We turn now to that rare tsunami advisory for the entire North American West Coast from Alaska to California.
Beneath the serene and endless blue of our planet's oceans lies a world far more dynamic and tumultuous than we ever imagined. Here, hidden from the human eye, are phenomena so powerful they can reshape the very foundations of the ocean floor. These are the stories of Earth's silent yet formidable architects, the turbidity currents, forces of nature that have not only sculpted the depths, but also hold secrets crucial to understanding our planet's past and future. What are the mysterious underwater phenomena revealed by the study of turbidity currents, and how do they reshape our understanding of the ocean's depths? The depths of our oceans have long been a source of fascination and mystery. Beneath the waves, a hidden world thrives, far from the reach of sunlight. One of the most astonishing discoveries in this enigmatic realm is the existence of turbidity currents, powerful underwater avalanches. These currents are not mere trickles of water, but immense cascades of sediment, laden with a mixture of sand, mud, organic matter, and even human-made pollutants like plastics and pharmaceuticals. Turbidity currents travel through the ocean's vast canyons, sculpting the seabed as they go. Their power is so immense that they can carve out some of the deepest and most extensive canyons known to us, rivaling even the grandeur of terrestrial canyons. A striking example of their might was witnessed in the aftermath of the 1929 Grand Banks earthquake. This colossal seismic event triggered an underwater avalanche off the coast of Newfoundland, Canada, reshaping the ocean floor and even causing a devastating tsunami. What makes these phenomena truly mysterious is their elusive nature. For centuries, these underwater avalanches remained hidden from human eyes, their existence only inferred from the aftermath of their immense power. But now, thanks to advances in oceanography and deep-sea technology, we are beginning to uncover the secrets of these underwater giants. Researchers are using sophisticated sonar imaging and deep-sea observatories to capture and study turbidity currents in action, revealing a world that is both awe-inspiring and vital to our understanding of the Earth. To really understand this, we have to look back in history. Catastrophic events, the oceans, in their vast and profound depths, have witnessed catastrophic events that have left indelible marks on our planet's history. Among the most dramatic of these are the underwater avalanches triggered by seismic activities, events so powerful they can alter the very topography of the ocean floor and even impact life on land. An unforgettable example of such a cataclysm unfolded in November 1929. The Grand Banks earthquake off the coast of Newfoundland, Canada, set off a chain reaction of unprecedented scale beneath the waves. The earthquake's tremors shook the ocean bed, dislodging massive quantities of sediment within the underwater canyons. This movement initiated an underwater avalanche, a turbidity current of immense proportions, rushing down the canyon at incredible speeds. The scale of this event was staggering. The sediment flow, equivalent in mass to twice that of Mount Everest, reshaped the ocean floor as it cascaded down, carrying with it an unstoppable force. In its wake, this underwater upheaval triggered a devastating tsunami, causing widespread destruction and tragically claiming the lives of over 25 individuals. This event was a stark reminder of the interconnectedness of our world, how a disturbance in the ocean's depths can bring about significant impacts on land. Geological significance. The geological significance of turbidity currents in shaping our planet's undersea landscape is profound and multifaceted. These underwater avalanches, often unseen, play a crucial role in sculpting some of Earth's most extraordinary geological features. As these powerful currents sweep across the ocean floor, They carry with them vast amounts of sediment. This process is not merely a transfer of material. It is a dynamic reshaping of the underwater world. Turbidity currents carve out deep canyons and gullies, creating intricate patterns and structures beneath the waves. The sheer power of these currents is capable of cutting through the seabed, forging channels and canyons that rival the grandeur of any on land. These formations are not just striking landscapes. They are records of Earth's dynamic history, revealing the ongoing processes that shape our planet. The comparison of these underwater canyons to their terrestrial counterparts is inevitable. Yet, these subaquatic features often exceed the scale of those on land, both in depth and complexity. Their formation is a testament to the relentless and often unseen forces that continuously mold our planet's surface. To understand the full scope of these underwater forces, we must not only consider their geological significance, but also recognize their profound impact on climate change. Impact on climate change. The role of the ocean, particularly the mysterious turbidity currents, in climate change is a crucial yet often overlooked aspect. These underwater avalanches are not just remarkable geological phenomena. They are also significant players in the global carbon cycle. As turbidity currents travel across the ocean floor, they do more than just transport sediment. They play a pivotal role in carbon sequestration, a natural process critical in mitigating climate change. These currents carry organic material, including carbon, deep into the ocean, effectively trapping it away from the atmosphere. The organic matter, both terrestrial and marine in origin, is swept along by these currents and eventually settles in the deep sea. Here, it becomes part of the sedimentary layers, locking the carbon within the ocean floor. This process removes significant amounts of carbon from the carbon cycle, reducing the greenhouse gas levels in our atmosphere. Scientists are now exploring the extent to which these submarine avalanches contribute to the reduction of atmospheric carbon. Each avalanche potentially transports vast quantities of carbon-rich sediment, highlighting the ocean's role as a carbon sink and its importance in climate regulation. While the impact of these deep-sea phenomena on climate change is significant, it's the technological breakthroughs in oceanography that are illuminating these mysteries and broadening our understanding. Technological breakthroughs. The uncovering of the ocean's hidden dynamics, especially the turbidity currents, has been greatly accelerated by technological breakthroughs in oceanography. These advances have opened new frontiers in our quest to understand the deep sea. One of the key tools in this exploration is sophisticated sonar imaging. This technology allows scientists to map the ocean floor in unprecedented detail, revealing the contours and structures shaped by turbidity currents. These sonar images have been instrumental in identifying and analyzing underwater avalanches. Alongside sonar, the deployment of ROVs and AUVs has been transformative. These remotely operated and autonomous vehicles can ascend to the abyssal depths, capturing real-time data and visuals of these elusive phenomena. Equipped with cameras and sensors, they bring back images and information from places previously unreachable. The data collected by these advanced technologies are analyzed using sophisticated software, providing insights into the frequency, magnitude, and behavior of turbidity currents. This analysis is critical for understanding not just their geological impact, but also their influence on marine ecosystems and global climate patterns. The technological advancements in exploring these underwater currents not only deepen our scientific knowledge, but also help us identify the often overlooked clues from infrastructure damages, revealing the hidden power of these marine forces. Clues from infrastructure damages. The discovery of the powerful forces at play in our oceans has often come from unexpected sources. One such source is the damage inflicted on underwater infrastructure, which has provided crucial clues to the existence and power of turbidity currents. The discovery of the powerful forces at play in our oceans has often come from unexpected sources. One such source is the damage inflicted on underwater infrastructure, which has provided crucial clues to the existence and power of turbidity currents. In several instances, engineers have observed ruptured gas pipelines and severed communication cables lying on the ocean floor. These disruptions, initially a mystery, were eventually linked to the immense forces generated by underwater avalanches. These incidents of infrastructure damage have occurred across various parts of the globe, painting a picture of the widespread influence of turbidity currents. The ruptured pipelines, initially designed to withstand the harsh conditions of the deep sea, bore silent testimony to the unexpected power of these subaquatic events. Scientists and engineers studying these occurrences realized that the patterns of damage were consistent with the flow of massive underwater sediment movements. This realization sparked a wave of interest and led to increased research efforts to understand and map these powerful underwater currents. While the clues from infrastructure damages highlight the sheer force of these underwater events, they also lead us to explore their ecological impact, shedding light on the intricate dynamics of deep-sea ecosystems. Ecological impact. The ecological impact of turbidity currents is as profound as it is varied. These underwater avalanches play a significant role in shaping the deep-sea environment, influencing the distribution and abundance of marine life. As turbidity currents cascade down ocean canyons, they transport not just sediment, but also nutrients and organic matter. This influx of nutrients is vital for deep-sea ecosystems, often sparse in resources due to the lack of sunlight. The organic matter carried by these currents serves as a critical food source for a variety of deep-sea creatures. From tiny microorganisms to larger marine animals, these nutrients support a complex food web, essential for the survival of many species. The deep sea, a realm once thought to be barren and lifeless, is teeming with life, much of it adapted to thrive in these nutrient-rich conditions. Turbidity currents, therefore, play a pivotal role in sustaining this hidden biodiversity. Recent studies have also revealed the role of these currents in shaping the genetic diversity of deep-sea populations. By connecting different parts of the ocean floor, turbidity currents facilitate the spread of organisms, contributing to the genetic flow across vast distances. Understanding the ecological impact of these underwater phenomena not only enriches our knowledge of marine life, but also paves the way for future research and its far-reaching implications for both science and environmental policy. Future research and implications. The journey to unravel the secrets of turbidity currents and their far-reaching effects is just beginning. Future research in this field holds immense potential, not only for advancing scientific knowledge, but also for addressing some of the most pressing environmental challenges of our time. The journey to unravel the secrets of turbidity currents and their far-reaching effects is just beginning. Future research in this field holds immense potential, not only for advancing scientific knowledge, but also for addressing some of the most pressing environmental challenges of our time. Scientists are now focusing on several key areas. One is understanding the frequency and intensity of these underwater avalanches. This knowledge is crucial for predicting their impact on both the oceanic ecosystem and human infrastructure. Another significant area of study is the role of turbidity currents in carbon sequestration. By quantifying how much carbon these currents transport and deposit on the ocean floor, researchers can better assess their potential in mitigating climate change. Technological advancements will continue to play a pivotal role. The development of more sophisticated deep-sea monitoring equipment and data analysis tools will enable scientists to observe these phenomena more closely and in real time. The implications of this research extend far beyond the academic realm. Understanding turbidity currents can inform strategies for protecting critical underwater infrastructure and managing ocean resources more sustainably. Moreover, it can contribute to global efforts in combating climate change, offering new insights into natural processes that regulate our planet's health. We hope you found these facts intriguing. If you've heard them before or have any thoughts to share, please let us know in the comments below. Don't forget to give us a thumbs up and subscribe to A World to Discover to join us on our journey of discovery.